Alright class, welcome back. Again, yesterday we talked about divergence and the k component of curl, and I started us off with Greens Theorem and explained that it's useful to change the flux and circulation line integrals into double integrals for easier calculation. The fields do not need to be conservative. So the normal form of Greens Theorem is also the flux form of Greens Theorem. So the flux of a field across C is equal to the double integral of the divergence over the region, the area. So what that looks like in terms of the integral itself. This was the original flux integral. It was the field dotted with the normal vector ds, which we actually had a different, we didn't ever use that version. It actually was equal to this. This is important right here, because you have to recognize this one here. It's m dy minus n dx. So again, this right here was outward flux, and this is going to equal the double integral over the area of the region of the curve of the divergence of f, which we found out yesterday was this value here, the partial with respect to the I component with respect to, the partial of the I component with respect to x plus the partial of the piece that's with the j component with respect to y. And then it's dx dy or dy dx, whatever way you have your bounds set up. So, right there, we can turn our outward flux into a divergence integral. These are equivalent statements, and I'm going to call this equation 3 in case we need to use that later. Alright, so again, this is outward flux. And so that's what you have to realize. When you see a problem and it starts off looking like this, you have to know, okay, I have to use the divergence integral, which is this one here. The tangential form, or the form for circulation, counterclockwise circulation of a field around C equals the double integral of the curl, the k component of curl, over the region. Hi Loki. My dog just jumped up onto the bed where I'm making this video, so I'm not paying attention to him. Alright, so anyway, the original form for this one was the integral of f dot t ds. We never used that form though. We used the form where it was f dr dt, f dot dr dt. But the form you also might see it in is the line integral around the curve of m dx plus n dy. So if you see this is counterclockwise circulation. If you see that, you can turn that into a double integral over the region bounded by the curve, and then it's the k component of curl, and we figure that out as the partial of the j component with respect to x minus the partial of the I component with respect to y, dx dy. So hopefully you guys see what we did yesterday now pops into these two integrals right here and right here. That's the divergence, that's the curl, k component of curl. Okay, so now let's show how these work. I'm going to just verify today that both of these work. Okay? Each way. We're going to do each form. You know what? No, maybe what we'll do is I'll let your assignment be to do the other one. So I'll do flux, and then your assignment will be to do circulation. Okay, so for flux the old-fashioned way from 7.2, we would use the integral up here. We would use the line integral, what just happened, of m dy minus n dx. Okay, so that's what flux is equal to. So now we have to parameterize this curve. Well, it is parameterized for us. This is m, this is n, And, oh, nope, that's a lie. I didn't read the whole problem. M is the field. N is the, M and N are for the field always. They're the components of the field, the vector field. This is going to be our X and our Y. So, to do this flux equation, M has to be parametrized, so M is going to equal X minus Y, so that's cosine of t minus sine of t. N is going to equal X, which is cosine of t. Dx is equal to negative sine of t, and dy is equal to cosine of t. So I got all the pieces to convert this. I know my t is going from 0 to 2 pi, so my flux integral will become an integral from 0 to 2 pi of m, which is cosine of t minus sine of t, times dy, which is cosine of t, minus n, which is cosine of t, times dx, which is negative sine of t. And that's all dt. Okay. So now I have to evaluate this. So we do some math. We get the integral from 0 to 2 pi of cosine squared t. And I believe that's it. Yeah, because these two cancel out. You'll have a plus sine cosine and negative sine cosine. Now, if you guys remember correctly, there's a conversion for this. It's 1/2 plus cosine of 2t over 2. I'm not going to do all that work, so convert and integrate. This integral will equal pi. So the flux is equal to pi. Okay? Again, the key is finding the 4 components and putting that in. Now, notice how this wasn't that bad the original way. And that's because the region is a nice unit circle. It's not a square or a triangle, so we don't have to worry about it. But I am going to now show you how to use the new method with flux. So the new method with flux, using the divergence integral, because these are equivalent, we have that the area over the region, that this flux should equal the area over the region of dm dx plus dn dy. And again, I'm using this one because it goes with flux, and I'm doing flux first. dx dy. Okay, so let's look up at this. Notice how we don't have to parameterize the curve anymore. What's the derivative of f of the I component with respect to x? Well, dm dx is equal to just 1. dn dy, if you look up here, is equal to 0. So we get that this integral turns into the integral over the region of 1 plus 0 dx dy, which is just the integral over the region of dx dy, and hopefully, or dy dx, it doesn't matter. What this means is this is basically finding the area of the region only. There's no other part to it. Okay, hold on one sec. My pen died. It's like class. Maybe I need to change the battery. So this is the area of the region. Well, what is the area? What shape is this? Well, it's a unit circle. What is the area of a circle? That's just pi times the radius squared. Well, what is the radius? Since it's a unit circle, the radius is 1. So the answer is that this is pi. Sure enough, it matches what we got doing it the other way. So both ways work for flux. So what I want you guys to do for your assignment, and I'm going to post this, is I want you to do the same thing. You can do it on this note sheet, or you can do it on a piece of paper. I want you to do exactly what we did, but I want you to do it with circulation. Therefore, I want you to prove that if you do this formula with this way first, with the counterclockwise circulation from before. So I basically want you to do this, and I want you to show me that it equals the k component of curl, which is this. I want you to do these two formulas with the problem I just did. So that'll be your assignment tonight. Okay? You can write it on this note sheet, fill it out, or if you want to do it on another piece of paper, you can just upload it on the Canvas assignment where I'm going to have the assignments. Okay, hopefully that works, and then I'll come back and we'll do a couple more problems for the last day of this week. I hope everyone's doing well. Goodbye.